Hi everyone, this is Ms. Becker. Welcome to week 4 of Discrete Math. I hope you guys had a good weekend. It was nice and sunny, and looking forward to hopefully some more of the same this week. If you read the week 4 plan, what I'd like to do is just kind of review one of the problems from last week's assignment. This one is question 2, and then do a little introduction to a new type of circuit called a Hamilton circuit. So on the left here was the vertex edge graph from question 2, and the directions we were supposed to do were to use the best edge algorithm to find a minimum spanning tree for the graph. So step number 1, which I didn't write down, is always to put the vertices on the graph, and then the next step is to add the minimum length edge. So in this graph, 3 is the minimum. So up here on the graph, I connected A to F, that was a 3, and I connected D to C, which was a 3. And from the directions of the algorithm, you can add both 3's because no circuit or loop was made. If we continue on with this, then the 5 would be the next minimum edge. So I also added the 5 from E to C. And that's okay since there's not also a circuit being made yet. If we keep going with that and find the next minimum one, which would be a 6, we notice that the 6 cannot be added since it would make a circuit. So the 6 is from E to D. So if I would add that in, then I just made a circuit or a loop that goes from E to D to C and back to E. So I cannot add in ED right now. All right, if I continue with that same graph up here, this out of the way. That out of the way. Okay, so at the top here, so there's the 3, and the 5, and then I just realized I can't add the 6. Okay, so if I continue on past the 6, then the next minimum ones would be the 8's, and there's an 8 from B to E, and there's an 8 from B to C. So I went in and I added the BE edge of 8, but I cannot add in the BC edge of 8 because otherwise I would make a loop again. So down here I just wrote you can add either one, but not both, since then it would form a circuit. So up here on the EB one, right, I ended up putting that over here on the left, what that would look like. And if I decided to add the BC8 instead, right, then I couldn't add in the EB because that would make a circuit. So this is when I end up with either this option on the left or this option on the right. And if we continue from those two options, so I kind of have the EB 8s over here and the BC 8s over here, then the next lowest number is 9. And it says that there are 2 9s. So there was one from A to B, and there was also one from E to F. So on the top 2 up here, I added in the AB 9, and I added in this AB 9 because that was from the 2 different 8s, right? The BC 8 and the EB 8. And then down here, I added in the EF 9, right, to both of these, and that was from the 2 different 8s, so the BE 8 and the BC 8. So what ends up, set away again, that there are 4 options. So these are completed since all the vertices are connected in some way, and so there's 4 options for the minimum spanning tree, and the total weight, if you add up the 3, the 9, the 8, the 5, and the 3, is 28. And you could check that for any of those 4. They would all add up to 28. All right, so I just wanted to review one of those problems in case I try to give everyone feedback via email on what they might have made errors on. But if you have any questions, right, feel free to email again. So moving on a little bit, we're still in Unit 2, Lesson 1, but this is the next activity. And we're going to look at a different type of spanning tree, and it's called a Hamilton circuit. And that seems to happen all the time. A dog barks. So just a couple things about a Hamilton circuit I wanted you to be aware of. This is actually, Hamilton circuits are used to solve a famous problem called the traveling salesperson problem, referred to as TSP. And it's actually an unsolved problem. And what that means is here in the red, unsolved means that there is not an efficient way to find a solution for any graph. So basically, sometimes it turns into like a trial and error because there's not really a set process. There's a couple options that you can try, and one of them is referred to the best edge algorithm, kind of like what we had before. And it's efficient, like you can follow the process, but it doesn't always find the solution, meaning the best answer for the problem. There is another option, it's called the brute force algorithm, and it always finds a solution, but it's not very efficient. It's basically about finding like all the options and then determining which one actually is the minimum. So that's why it's not considered very efficient. And we'll come back to this. We're going to try one of these algorithms and then look at why it maybe didn't work as well as it should have, or we would hope. So we're going to use these algorithms to find a solution to what's called the traveling salesperson problem. It's considered a famous problem in discrete math. And basically here's a statement of what the problem is. It's about a salesperson, and if a sales representative wanted to visit several different cities and go to each city exactly once and then return home from where he started, among the possible routes, which one would minimize the total distance that the salesperson would travel? Now, it's called the traveling salesperson problem, but it can be presented in different contexts. So it says, although the TSP, the traveling salesperson problem, is classically stated in terms of salesmen, cities, and distance, it also refers to similar problems in other contexts. Consider the TSP in the context of this airfare graph. So what we're going to do is we're going to try to solve the traveling salesperson problem for this graph. And the first question it asks is, what does weight represent in this case? So if you take a look at the edges here, they're written in dollars, and it's about airfare. So we could say that like this edge of 277 is really representing the cost of the airfare from Minneapolis to Chicago. So what am I trying to find? I'm trying to find the least expensive route to get to all these cities and back to where I started, using the costs that are indicated on these edges. So I'm trying to minimize the weight so that my cost is the lowest possible. Oops, sorry, I had to click in here. Yep. So what does weight represent? It's the total price to fly to all the cities and end where you started. Okay. So here's kind of what the solution to that problem looks like. So what we're trying to do is find a route through a graph that starts at one vertex, visits all the other vertices exactly once, and finishes where it started. That's what's referred to as a Hamilton circuit. So when we solve this problem, we have found a minimum weight Hamilton circuit for this graph. It's got kind of the same language as a minimum spanning tree, but Hamilton circuits are a little different because you have to get back to where you started. Whereas the spanning tree, we just had to make sure that we were including all the vertices in some way. So this yellow highlight is actually showing a solution to this problem. And what it says is, if I would start in Minneapolis and then go to St. Louis and then go to Kansas City and then go to Chicago and finally back to Minneapolis, if I add all those up, the total airfare is $742, and that actually ends up being the cheapest route. So if you tried to find a different route and hit all four of those, you wouldn't end up finding anything less expensive than this. This is actually the solution to this vertex edge graph. One thing to note is you could start and end at any of the cities and still follow this route. That's not considered a different circuit. It's only considered different if it had different edges. It does not matter where you start or which direction you go around. So I could think of this highlighted path as maybe going from Chicago to Kansas City to St. Louis to Minneapolis and then back to Chicago. It's still the same Hamilton circuit because it followed all the same edges that I did in the first place. Okay. So we are going to talk through the strategy that can help us find that Hamilton circuit. And it's kind of a variation of the one that we used for minimum spanning trees. So here's the algorithm. Step one is make a copy of the graph with the edges drawn lightly. I just recreated the graph up here, and it says darken the shortest edge. I'm actually going to just do highlighting for the shortest edges as I go through these pages here. But you know, if you didn't have a highlighter, you could definitely follow what they're saying a little bit more with drawing the edges lightly and then darkening them. So we're going to be darkening them as long as we do not create a circuit of darkened edges or highlighted edges, unless all the vertices are included, and no vertex can be touched by 3 darkened edges. The edge you darken does not have to be connected to previously darkened edges. Okay, and then we just keep repeating step 2 as long as it's possible to do that. Okay, so this is a little more complicated algorithm. So what I just said is I'm going to highlight instead of darken the edges. And what I'm doing is starting with the shortest edge. So 78 is the smallest value edge here, smallest weight. So I'm just going to highlight from Kansas City to St. Louis. So that's starting with the smallest edge. Okay, then after that one, so now I'm looking for the next shortest edge, which is 113. All right, and I can highlight that as long as I do not create a circuit of highlighted edges, so I did not create a circuit there, and no vertex is touched by 3 highlighted edges. So if I look at this vertex, there's only 2, right? There's only 1, there's only 1. So that's why I can go ahead and add in that 113. Now, what happens here if I try to do the next shortest edge, which is the 116? And the reason I cannot add it in is because even though it's the shortest, I would create a circuit of highlighted edges. Again, remember I'm using highlighting instead of darkening. So right there, I just would have created a circuit. So I can't include the 116. Okay, so if I move past the 116 to the next smallest one, which would be the 271, right? I cannot add that one either because it would, even though it doesn't create a circuit, it creates a vertex that would be touched by 3 highlighted edges. So like right here at St. Louis, I just touched that vertex 3 times. Okay, so again, I won't be able to add in the 271. So I go on to the next shortest one, which is the 277. And actually the other one that's left is also 277. So there are two edges of 277. So I just picked one since neither one, right? So if I went with this highlighted one from Minneapolis to Chicago, it didn't create a circuit and it didn't create a vertex that would be touched by three highlighted edges, right? Because this vertex is only touched by two, same with this one, and one. So it's okay to add that highlighted edge in, right? Then only thing I have left is the other 277, and I can go ahead and add that one in because again, it does not create a circuit, right? Oh, I'm sorry. It does create a circuit, but it's all the vertices are included now, okay? And still no vertex is touched by three highlighted edges. So because it's that last vertex, it's okay to create a circuit now. Okay. All right. If we add up these four edges, we actually get a minimum weight of 745, which we know is actually not the minimum weight of that's possible, because we actually found a different solution, or we talked about a different solution before that had a total weight of 742. So obviously 745 is bigger than that. So this is the problem with the best edge algorithm. It doesn't always give us the right solution. So here's kind of our reminder from the beginning, right? That this process involves us trying to find a Hamilton circuit, and that the best edge algorithm, although it's efficient, like we kind of can follow through its steps, it doesn't always find the solution, right? So what we are going to do is kind of look at the other option, which is called the brute force algorithm. So remember, this one, it said it works, but it's not very efficient. And this algorithm kind of explains why it's not very efficient. Because what you do is you find all possible Hamilton circuits, and then you compute the weight of each one, and then you choose the minimum weight Hamilton circuit. So basically, if it was a very complicated graph, you would be finding potentially a lot of Hamilton circuits, right? So it's not so much of a step-by-step to get you to the right answer. It's more of a find all the answers possible and then figure out which one is actually the best. Okay, so just to kind of show you, this problem, this graph ends up having three Hamilton circuits. So we've already talked about two. This is the one that we talked about first that gave us that 742 airfare total cost. And then the one that we just kind of found by doing the best edge algorithm, it did give us a Hamilton circuit, but its weight was 745, so it just wasn't the minimum Hamilton circuit. And then down here in the bottom, this is one more Hamilton circuit. And the reason, we know it fits the definition is it hits all the vertices and finishes where it started. So like if I went from Minneapolis to Kansas City to Chicago to St. Louis to Minneapolis, right? So this is actually different than the other two. But if I calculate its airfare, it ends up being $777, which isn't the best option. Okay, so the brute force process would just say, find all the options, calculate their total weight, and then the one that's the lowest would be the best, or is the solution to the problem. Okay, so I know that was probably a lot of me talking, it felt like it, but I would like you guys for this week just to try one problem. So this is your assignment. It's also in Schoology with this picture and with these questions. And the directions are to find a minimum weight Hamilton circuit for the graph below. You can use either the best edge algorithm for finding a Hamilton circuit or the brute force algorithm. Remember, the best edge algorithm may not always find the solution, but that's okay for now. I just want you to try the process. Make sure your graph does touch all the vertices once and returns to the same vertex. That's what it needs to do to be a Hamilton circuit. Okay, so I'm going to kind of let you guys go now with that. Again, this picture and these 3 questions are also in Schoology, so you could either, go there and do this question now, or you could write this on a piece of paper and enter it in Schoology, or just email me the paper. Either one is fine. So good luck. Remember to email with any questions. This is kind of a pretty advanced process, I guess, we're doing here. So I'll completely understand if there's issues along the way. So, all right, take care, everyone. Bye.